So notice that the problem set for the first, for you juniors, is due on the first. Jordan, you don't have to do that. Yep, you heard of me. We had finished the first, or section 15.1 before break. Were there any questions on like 1 through 16 or anything that came? Anything there before we jump into the new stuff? If you haven't done anything yet, or you're just not sure, we can always do it. You know, you can always ask questions again later. Not a big deal. Doesn't have to be today. But if you have something that you're like, hey, I was working on this and I didn't know what to do, you can certainly start there. Okay, no big deal. Again, enjoy your break. You didn't need to do anything. That was the point of having it due on the first and not, you know, the Sunday we come back from break or something. Hi, Miss Williams.
On special delivery.
Oh, goody.
Isn't that wonderful?
That's gotta be for me.
No, well, we have one for Amanda Roth,
Couple for
2 for Amanda Roth,
Whoa.
3 for Amanda Roth,
Yeah.
and another for Margot.
Whoa.
That's the South Africa.
It is not related to South Africa.
Margo, open it, man. Right now.
Resident check.
All right. So let's jump in here then and get started. So in section 15.1, we had defined an exponential function and a logistic function and done a little bit of application there. In section 2, we're going to continue doing some more applications. So one application for exponential functions is using them to model population. So the model that we'll use to describe exponential population is this exponential population model. Is P of t equals P naught times 1 plus r over 100 to the t. Where P of t is the population at time t, P naught is our initial population, R is the rate of change written as a percentage, and T is the time where the unit for your time t should be the same as that for R. Everybody so far so good? So if we look at this population model, and we remember that from section 1, an exponential function was in this form, right? Everybody agree with that? Again, where b is positive and not equal to 1. That means that this 1 plus r over 100 is essentially our b in our exponential. Everybody agree with that? Okay. Do you remember how we can tell if something is exponential growth or decay? You could tell just by looking at the B. So again, if your B value is bigger than 1, your exponential growth, and if your B value is between 0 and 1, it's decay. That's assuming for the A value positive, which is the one we'd be talking about, because if we're talking about population being the same as our A, nobody's initial population is going to be a negative number. That doesn't make any bit of sense, right? Okay. So that's just a little bit of review, kind of wrapped up in this new definition. So let's do a little example here. Okay, so here you're given two population models, and we're going to ask whether they are growth or decay, and then to find the constant rate of growth or decay. So for part A, what are we looking at to determine if this is growth or decay? The value for B, which in this case is which number? Yeah, this 1.03, yada, yada, yada. So is this one growth or decay? Growth. And for part B, we're looking at this number, which means it's decay. Easy enough, right? The second part of the question asks you to find that constant rate of growth or decay. Basically, that's asking us for the value for R. So if we look above, what we noticed is that 1 plus R over 100 is the same as B. So I can say 1 plus R over 100 is equal to 1.0384. Everybody feel cool with that? So we can solve by R by subtracting the 1 and then multiplying by 100. Feel good there? Part B, we can do the same thing. So 1 plus R over 100 equals 0.9867. And again, subtract 1 and multiply by 100, and we get negative 1.33% for R. Can we make an observation here about the value for R and whether these are growth or decay? Good. If R is negative, it's decay, and if R is positive, it's growth. That holds true always, not surprisingly, right? Everybody feels cool with that observation? So far, pretty simple, right? We just used like some basic formulas. We cool? A little bit of easy algebra. Okay. Let's do another example. Again, in this section, really all the work we're going to be doing is going to be these application story problem kind of situations. So I'm just going to be kind of like copying and pasting stuff in. Okay. So it says here in the next example, determine the population model with an initial value of 15, increasing at a constant rate of 6% each year. It tells us we're using the population model in the question. Okay. So I'm using this. Whenever we write a model, we need to make sure we have a dependent and independent variable inside the problem, so nothing is going to get filled in for P of t or t, which means what we have to still fill in is our value for P naught and our value for R. What should our value for P naught be? 15, because P naught is the initial amount, and our value for R should be 6, which is our rate of change as a percentage. And if I simplify that down, 1 plus 6 over 100 is 1.06. And I should probably state that t is in years here, since the rate was every year. Pretty easy, right? We're just filling stuff into a formula. You just have to remember a little bit of the vocab and what the symbols are representing, but overall, not too difficult. Let's do another example. Okay. So again, determine the population model. So it tells us the model we're using. So again, initial value of 15, increasing at a constant rate of 6% every 6 months. So again, my P naught and my R are still the same. What's the only difference here between this problem and the previous one? Yeah, the rate is happening every 6 months as opposed to every year. So how are we going to account for that? It's going to be how we write the t in the exponent. So first thing we should do is we should pick a unit for t. There's really 2 appropriate units that we could use. What would those 2 units be? Okay, so one could be in months, and the other would be in years, right? So, okay, let's do the years one first. So, we're having a rate of change happening every 6 months, right? How many rates of change happen in 1 year? 2. So instead of writing t, I'm going to write 2t. Okay? How much of a rate of change happens in 1 month? What was that? 1/6, right? If we're getting 1 rate of change every 6 months, in 1 month, we get 1/6 of a rate of change. So instead of writing t, we're going to write 1/6 t, or I'll just write it as t over 6. Either of these 2 answers is appropriate. Depending on the question, they may ask for, write the model with t in years or months, in which case one of them is correct and the other is incorrect. But in this problem, there's no designation as to which one they would want. Either is appropriate. You do not need to give both, unless the directions ask for, multiple models because of wants it, the model with t in years and the model with t in months or something. It would just be a directions issue. But either of these are correct, are a correct model. Everybody cool? No big deal. Next example. Again, if we're doing something and you don't understand it, or you don't get it, or you don't like what we did, or you need a follow-up question, make sure you stop and ask. No problem at all. Next one, suppose that a colony of 120 bacteria is put into a petri dish and doubles every 3 hours. Predict how long it would take there to be 400,000 bacteria. When I read this question, I see really two questions in here. So this first part is asking me to write a model for a situation. And then the second part is asking me to solve that model for a particular instance. Everybody okay with that idea? So we'll start by dealing with the first part and writing our model. Now, from the context of this question, it should be clear that the model we need to use is the population model. Why? Talking about the amount of some living thing that's reproducing, that's population, right? Should be like super obvious that that's what we would need to use. Again, most of the difficulty here is going to be like in the reading comprehension side. So I just want to make sure that like when I'm making these decisions, I'm just making sure we're all clear as to why we're making these decisions. You know what I mean? Because it's not like the difficulty in this section is not going to be the mathematics. It's going to be like the decoding words into symbols part. So I just want to make sure that we're being really obvious as to how to do that. Okay, so our model, what are we putting in for P naught? 120. What are we putting in for R? What word is giving us our R, or is telling us about our R? Doubles, okay? So what percentage does doubles mean? Okay, let's ask a different question. So say we have 2, and then we go to 4, right? That's doubling. What percent of 2 did we have to add to 2 to get to 4? 100%. Everybody agree with that? So doubling implies that the percent change is 100%. Again, the difficulty there was the reading comprehension of like, what does doubling mean as a percentage? That's why we're talking through it. But when I phrase it as that, like, we're going to 2 to 4, what percent change is there going? It's like, oh, okay. Yeah, sure. That makes sense. All right. And then this is happening every 3 hours. So what unit for T would you want to write this in? I agree, in hours. So how much of a rate of change happens in 1 hour? 1/3. So instead of T, we'll write T over 3. Okay, so there's our model. Notice that if I simplify this down, 1 plus 100 over 100 is just 2. And boy, that looks a lot like doubling now, doesn't it? Okay. To do the blue piece, we're going to be asking how long. So what are we solving for here? Okay, we're solving for T. So we need to then plug in a value for P of T, which should be 400,000. So to solve this, we're going to go to the calculator. So the left-hand side is one of my equations, and the right-hand side will be my other equation. Notice I'm just in regular old function mode. Doesn't matter degrees or radians because we're not using sine or cosine at all. Everybody's cool? Before I hit graph, though, I need to set my window. So if I think about this, in 3 hours, we're going to be at 240. In 6 hours, we'll be at 480. In 9 hours, we'll be at 960. I don't know. It seems like it's going to take a long time to get to 400,000. I'm going to go all the way up to 100. It's probably more than I need, but if it's not enough, I can always go back and extend that out. The Y is representing the population. The minimum population is 120. That's what we're starting with. I'm just going to use 0 because it's a round number. The biggest population we care about is 400,000. I'm going to set my max Y at 500,000 though, so I can make sure that I can see, you know, so that the 400,000 line isn't just at the top of my viewing window. And then I'll go up by 100,000s, I guess. Let's hit graph. There's my 400,000 line. Here's my population curve. Whoa, that got steep real quick. Guys, doubling is fast. All right, so what I'm looking for is the intersection of those two curves. Second trace, intersect command. Since there's only two lines or two curves and one intersection, I can just press enter 3 times. And it happens at about 35.11 hours. But still, pretty easy question, right? The part was probably the hardest was the doubling piece. But again, like it's just a, you know, like a grammar decoding kind of question, not so much a, you know, like a math difficulty. All right, another application that we can use exponential growth and decay models on is radioactive decay. Do you guys talk about radioactive decay in your chemistry class? I think a little bit was the common answer I've gotten from the other sections. Like maybe a little, but we don't really remember. It's okay. So radioactive decay, in essence, you have some substance, and over time that substance loses subatomic particles to turn into a new kind of substance. That's a pretty dumb definition, but I'm going to try to do this without any chemistry talk because it sounds like you didn't really do it, and not everybody's taking chemistry, maybe. I don't know. Anyways, we measure the rate in which radioactive decay occurs using something called a half-life. What the half-life is saying is it's the amount of time it takes for half of the original substance to decay into that new substance. When we talk about a half-life, that's talking about the rate, so it's giving us our value for R. What percentage value for R would half-life imply? So 50%. Okay, but is this, what type of exponential function is this? Decay, so it should be -50, yes, very good. Everybody cool with that? So this is the big takeaway. Otherwise, we can just treat this as a population problem. The only thing we need to remember is just that half-life just means R is -50. Okay, well, let's rock and roll. Here's some examples, or an example at least. I think I only just do one, because that feels like enough. Particularly if it's like the same as all the other ones. All right, suppose the half-life of a certain radioactive substance is 35 days and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. So again, radioactive decay problems we can treat as a population problem. Again, I'm going to start by thinking of this as two problems. The first problem is write the model, and then the second problem is going to be solve that model for a specific situation. Of course. So far, so good, peeps? So the initial amount, the P naught, is 10. The R is negative 50 because it's a half-life situation. And this is the half-life is happening every 35 days. So instead of T, we should write T over 35, where T is in days. And if we simplify that down, 1 plus negative 50 over 100 is 0.5. Boy, that sure looks like a half now, doesn't it? Okay. And again, it's saying find the time. So we're looking for solving T. So what are we going to plug in for P of T? 1. Okay. So to solve this, we're going to graph. So 1 goes in the 1 equation. 10 times 0.5 to the x over 35 goes in the other equation. And then we'll set our window. Let's think a little bit about the x. So we start at 10. After 35 days, there's 5. 70 days, there's 2.5. 105 days, there's 1 1/4. 140 days, there's 6 or 0.62 something, 0.625 or whatever. So it's going to be between 100 and 140. So I'll go up to 150. Since it's decay, the minimum value is going to be 0. It'll just, it's the least amount of it's stuff that you can have is none. It starts at 10, so that'll be the maximum value for decaying down. I'll go by ones. Let's hit graph. There's my 1 gram line. Here comes my decay function. There's the intersection I'm looking for. Second trace, intersect command, enter, enter, enter. And I get about 116.27 days. Feel good there? No big deal, right? So again, these exponential decay or radioactive decay problems, any different than the previous ones? Nah, man, not really. It's still the same thing. Now, remember from last time, or maybe you don't, we talked about the exponential model maybe not always being the best model to describe for a population or to model a population. And this logistic model maybe is a little bit better of a better fit for what's actually happening in reality. So let's take a look at one of these situations again. So in a situation where we're going to use a logistic model, you'd have a situation like this where I give you the model in the problem. I wouldn't ask you to build your own. Is everybody okay with that? That's a relief, right? One less thing. So you start a bunny petting zoo. What an entrepreneur you are. You're really putting the manure in entrepreneur there because it's a zoo and you're going to have to clean up poop. Yeah. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. Part A asks, how many bunnies do you have initially? Part B, what is the maximum sustainable population of bunnies on your farm? And then part C asks, how long will it take for you to have 500 bunnies? Well, we'll just hit these one at a time. So first things off, part A asks, how many bunnies do you have initially? Initially means what time? What would initially imply as a time? 0, right? Before anything's happened. That would be initially, right? So all I need is to do B of 0. And I hear people getting their calculator out. You don't need a calculator to do this. Negative 0.5 times 0 is 0. E to the 0 is 1. 1 times 99 is 99. 99 plus 1 is 100. 800 divided by 100 is just 8. Now, certainly there are cases where that calculator might have come in handy. In this case, it wasn't necessary, but I'm just teasing you guys, you know. Anybody feel cool there? Part B asks for the maximum sustainable population. What is that really saying? That's asking for the upper bound for this logistic function. Remember, a logistic function has like two asymptotes that it's kind of like stuck in between the upper bound and lower bound. Everybody that look familiar now? So the lower bound happens at y equals 0. The upper bound happens at y equals c, where c is the numerator of our logistic. So part B is just going to be 800 bunnies. No mathematics needed. I did it all through just definitions. That's nice. You know? Alternatively, if you had graphed that logistic model on your calculator and just looked at what the population was going over time, it probably would have been pretty clear that it was bounded by 800. If you forgot. Everybody cool? So far, so good? Part C asks for how long? What are we solving for here? T. Will it take to have 500 bunnies? So we're plugging 500 in for B of t. And then we're just calculator time, my dudes. Let's see, 500. And I'm going to use the fraction command here because I don't want to muck around with all the parentheses to make sure that this is actually doing what I want it to do. So I'm just going to use that fancy fraction command that I've shown you about 100 times now. If you don't remember, that's alpha y equals, and then pick the first option is the shortcut to find it. So there's that. I'll set my window, I don't know, 0 to 100 is probably appropriate. Rabbits have a reputation for reproducing quickly, right? There's some like colorful idioms about the frequency in which bunnies like to reproduce. The logistic we know is bounded, it has a lower bound at 0, so that makes a good y min, and upper bound at this value for c, so 800, that makes a good y max. And I don't know, going up by 100 seems appropriate. Let's hit graph. There's my 500 line. There's my logistic curve. Holy smokes, that happened pretty quick. It's almost like those bunnies, those idioms about bunnies were appropriate there. We'll do the intersect command, enter, enter, enter. and we get about 10.2 years. Everybody cool? So far, so good? Not too bad, right? All right. That'll wrap up section 15.2. We'll start 15.3 today, or maybe even finish. I don't know. We'll see. So up until this point, all these exponential equations, how have we been solving them? With the graphing with the calculator and finding the intersection, right? From Algebra 2, what do we know is the other way we could use to solve these? Logarithm. Guess what we're going to introduce today? Logarithms, yeah. So let's just start with our definition. So our standard definition for a logarithm is saying, okay, we have some exponential equation, like b to the y is equal to x. Because this is an exponential equation, we know that that b value has to be positive and not equal to 1. But let's go a little bit further. I want to say something else here. So if I take a positive number and I raise it to some power, what can I say about the result? What kind of number do I have to get back? Another positive number, right? So I can say x here is going to be, has to be positive regardless of what y is. Okay. So our standard definition for a logarithm is that I can translate this exponential equation into a logarithmic equation where all of the same attributes from our exponential equation travel over. So what is a logarithm really saying? It's saying it's the power of b that gives us x. So the name for that value of y, that power of b that gives us x, is just log base b of x. Okay with that? The big takeaway here, though, is that the x has to be positive. We cannot take the logarithm of a non-positive number. So log of 0, undefined. Log of a negative number, undefined. That's a name becomes super important as we get into using or solving logarithmic equations and using logarithms to solve equations. A little bit in the future, but that piece there is, I just want to make sure I hammer that pretty good here because it's an important piece there. All right, let's just do a little bit of practice getting used to this definition of logarithms, and it'll also help us review some properties of exponents, which is always a good thing to do. So we're going to just evaluate some logarithms without the use of our calculator. So let's say we want to do log base 4 of 16. So I can think about this as equal to x to make a logarithmic equation. I can then translate this into an exponential equation. 4 to the x has to equal 16. Well, in that case, it's pretty clear that x is just 2, because 4 squared is 16. Everybody feel okay there? So again, the base of the logarithm becomes the base of the exponential. The answer of the logarithm is the exponent. And the argument for the logarithm is the solution to the exponential. maybe color coding it like that is often helpful to really kind of get a feel for where the numbers are going. How about log base 5 of the square root of 5? Well, just like before, we're going to make a logarithmic equation by saying that is equal to x. And then we're going to rewrite that as a exponential equation. So I have 5 to the x equals the square root of 5. What do I do with that? No. 1/2. Remember that the square root of 5 is the same thing as 5 to the 1/2. So again, the property that we use there, let's write that a little bit better. Right, was the nth root of x is equal x to the 1/n. So let's say we have log base 3 of 1 over 27. Again, I'm going to start by setting it equal to x to create a logarithmic equation. That's going to translate into what exponential equation? 3 to the x equals 1 over 27. Okay. So I recognize 1 over 27 is 1 over 3 to the third, right? And then I know that the negative exponent property says that a negative exponent makes a reciprocal, right? So I can call that 3 to the negative 3. So the reciprocal of 1/3 and then move a negative into the exponent. Because if I do both a reciprocal and a negative exponent, it's like doing nothing at all, right? So what does x have to be then? Negative 3. Okay, let's say we have log base 12 of 1. Again, we're going to make that a logarithmic equation, which I can then recast as the exponential equation. As what exponential equation? 12 to the x is equal to 1. What's that tell me that x is? 0. Good. Again, remember that any non-zero number to the 0 is equal to 1. You guys okay with me just putting in blue the exponent property that I'm using below, just as a reminder? I know that you guys probably remember a lot of these, but if you didn't, it's just good review. All right, last example here. So log base 8 of 8. Again, I'll set that equal to x to make a logarithmic equation. Recast that as what exponential equation? 8 to the x equals 8. So what's x? 1. And that's pretty straightforward, right? No questions on that one. That's a no-dir. All right. So some observations based on what we just saw there. First one, log base b of 1 has to equal 0. Always, right? Because b to the 0 is equal to 1. And since I know b is the base of an exponential, or the base of a logarithm, it's positive and not equal to 1, so I don't have to worry about the 0 to the 0 possibility there. Everybody's cool? Second piece, or second observation, log base b of b is equal to 1. Very good. Again, if I recast that as an exponential, that's just saying b to the first is equal to b. No doy. Next one, log base b of b to the y is equal to just y. Again, if I recast that as an exponential, that's saying b to the y is equal to b to the y. All right. Yeah, of course it does. It better anyways, right? This is what we saw in part A when I saw like log base 4 of 16 was equal to 2. Right? Log base 4 of 4 squared is 2. That's what we're seeing. I just want to remind you that, like, yes, that's like clearly this is true, but where did we see, how did I observe that from doing the previous examples? That's where you're supposed to pick that up. Or alternatively, C or B. All right, last observation. B to the log base b of x is x. Great. So that's an exponential equation, right? So if I rewrite that as a logarithmic equation, I have log base of the exponent, or base exponent of the argument is equal to the exponent, which log base b of x better sure as heck equal log base b of x, right? So going forward, when we get into the solving, which we'll probably not get to today, these two pieces, or these two observations are really critical. What we're seeing in the first observation is that log base b is canceling the exponent base b. So we can use a logarithm to cancel an exponent base. In the third or the fourth observation here, we're seeing that an exponent base can cancel a logarithm. So we can use an exponent base to cancel logarithm when we're solving. Okay? So those two going forward are going to be super helpful to us. There's two special logarithms. The first is called the common log. That common log is log base 10, but we don't write the 10, we just write log with no subscript, and we'll understand that to be log base 10. Just like when we write a square root symbol, we don't put the index in there even though we recognize the index to be 2, right? The other special one is the natural log. That's log base e. And again, we don't write log base e, we write ln, and just recognize that to be log base e. When is it going to be really important that we remember this? When we're solving logarithmic equations that involve a common log or a natural log, so you know what exponent base to use to cancel the logarithm, right? So we really have to make sure we remember those because they are super duper important. Okay. You'll notice also that your calculator has built in a button for common log and for natural log already on it. So if I wanted to do the common log of 1,000, that should give me, before I press enter, this was a mental math problem. 1,000 is 10 to the third, right? So log base 10 of 10 to the third should be 3. Or if I wanted to do the natural log of 7, is that one we can do in our head? No, because there's not an easy way to rewrite 7 as a power of e. That's just some crazy decimal. Cool? Okay. Next up, I want to talk about the properties of logarithms. There's going to be 4 properties of logarithms that we're going to talk about. The first one is the product property. So what the product property is saying is that if I have multiplication inside my logarithm, that's going to turn into addition outside of my logarithm. And now that seems kind of strange, but it's really the same property that we saw for exponents, right? If I multiply 2 exponents with the same base, I add the exponents. So what we're seeing here would be multiplication outside the exponent turns into addition inside the exponent. And since exponential and logarithm equations are related, as we discussed earlier, it's not surprising that this property of exponents translates into a similar property for logarithms. Is that cool? The quotient property is the next one. So we have log base b of x over y. Hopefully at this point, this would not be surprising to see that this is going to be log base b of x minus log base b of y. Again, you're seeing that division inside the logarithm turns into subtraction outside the logarithm. What property of exponents is this analogous to? Well, the quotient property, right? Oops. Probably need to say that. So x to the a divided by x, or a to the y. But I'm saying all kinds of the letters wrong there. A to the x divided by a to the y is equal to a to the x minus y. Again, division outside the exponential turns into subtraction inside the exponential. These seem less weird when we link it to these properties of exponents that we're already pretty comfortable with, right? Hopefully. Next one is the power property. So log base b of x to the c equals c times log base b of x. So you're seeing a exponent inside the logarithm turns into a coefficient outside the logarithm, or multiplication outside the logarithm anyways. Let's put it that way. Which property of exponents is this one related to? So here you're seeing an exponent outside the exponential turns into multiplication inside the exponential. And then the last one, these first three are ones that we'll actively use in class for a lot of different kinds of problems. The fourth one was something that was super important when Mr. Kulik was a student and is now, based on the calculator technologies, almost worthless to you guys as students. It's called the change of base formula. So what this says is that log base b of a is equal to log base c of a divided by log base c of b. So what the change of base formula says here is this value for c, I can pick. So back when Mr. Kulik was a student, you either had a very simple scientific calculator, was pretty standard, where maybe it had log or natural log on it, or you didn't even have that, you had a 4-function calculator, which for most of your mathematics was probably the case. What did we do with, how would we do a logarithm problem? If I wanted to do like log base 2 of 3, I would rewrite this as common log of 3 over common log of 2. And then I'd go to the back of my textbook, find my table of logarithms, look up the value for common log 3, and then common log 2, and then type those into my 4-function calculator to divide them. That's what mathematics looked like not that long ago. By the time I was like an upperclassman, like a senior, had a calculator with log on it, was probably common enough, so you could do just like log 3 divided by log 2 on your calculator. But it was not until like these graphing calculators became common that you could do something like math, scroll to the bottom, find the log base, and you can just type in like log base 2 of 3 in your calculator and press enter and not have to hassle through the change of base formula. But the change of base formula was like a requirement. We had to have this to do anything not that long ago. Like in my childhood, this was like critical mathematics instruction that is now less critical because the calculator can handle it. Anyways, that's enough about Mr. Kulik's life. Let's, for grins here, prove one of these theorems. Let's do the product prop. So I'm going to define, just say let. I'm going to define capital A as log base b of x and capital B as log base b of y. Okie dokie. I'm going to use my definition of a logarithm to rewrite these as exponential equations. Cool there. No biggie, right? I'm going to take these two equations and multiply them together. So I multiply the left-hand sides together and then multiply the right-hand sides together. I'll use my multiplication property for exponents. So b to the a times b to the b is equal to b to the a plus b, giving me now a single exponential equation. Everybody cool? What am I going to do with this? Use my definition of a logarithm again. So that gives me log base b of xy equals A plus B. Everybody still doing good? And we're almost done because what is A equal to? It's log base B of X. And what is B equal to? That's log base B of Y. So we're done. I think in the homework set, we ask you to prove some of these other properties. You use a similar technique where you're going to start by writing a logarithmic equation with the pieces that you need, translate them to exponentials, use the property of exponents to do the combining, and then translate the result back out using the definition of a logarithm. So it should be very similar pattern to what we saw here. I'm sure somebody will ask about those when it comes time to do questions from the homework, so it's fine. And this feels like a good stopping point. I think this is where I stopped for the other classes, so we're just a few minutes ahead because you guys didn't have any questions, but that's okay. All right. So at this point, we should be able to do 77 up to, let me double check here.
You mean 17?
17 to 70? Yeah, I wrote the wrong number up there. Yeah, but the next block of problems wouldn't be due till the following Sunday. Yeah, because we wouldn't have had a chance to ask questions about them. Aiden's got the pattern figured out.